So, good afternoon, everybody. Welcome to the lecture by Laura Bégon-Lours on Neuromorphic Electronics with Oxides, from materials to hardware AI. My name is Jürg Leuthold. I'm the head of the Electronics and Information Science Department, and I'm proud to introduce you to the lecture of Laura. Now, let me make a short introduction. Laura got her master's degrees in 2012 in Engineering Innovative Technologies from the École Polytechnique Palaiseau in France. And then in 2017, she got a PhD degree in physics from the Université Pierre et Marie Curie, also in Paris, France, in the School of Physics. From 2017 to 2019, she was with the University of Twente. She performed research on inorganic material science in the respective group on inorganic material science at MESA Plus. And in 2019, she was awarded the Marie Curie Fellowship. She was then with IBM Zurich in Ruhr-Schlickon. Now, since 2023, she's with the Nano TCAD group with Mathieu Lusier in our department. And as of 2024, she was awarded an SNF professorships. There, she's now heading the Neuromorphic Electronics with Oxides group. She's a group leader there, affiliated in the Integrated Systems Laboratory in our department, the DITED department. Besides her research, she's also engaged strongly in activities of our community. So, for instance, she's the chair of the Swiss IEEE Electron Device and Circuit and Systems chapter. She's engaged in other activities. So, for instance, she's the editorial advisory board of the American Institute of Physics publishing for the APL machine learning. In the next few minutes, we're going to listen to the talk by Laura. Towards the end, there is no question and answer session. We directly move on because we would like to directly interact then with Laura. Maybe she's offering us something after that. Laura, the word is yours.
Thanks.
Stage is, please.
So thank you very much, Jörg, for this very kind introduction. It's actually really a pleasure for me to give this lecture today. I really enjoyed preparing this slide, giving actually an overview and also reflecting on what has been my journey so far. So just to let you know, I'm really happy today. The title of my lecture, as I said, is Neuromorphic Electronics with Oxides. We'll see how it covers pluridisciplinary topics from materials to AI hardware. So let's start about a few words about AI. I guess some of you are familiar about this topic. But I think what makes artificial neural networks so popular is that they surpass human capabilities in the tasks of really capturing very complex data structures. And with respect to this, AI really finds application in a wide variety of domains: healthcare, infrastructure monitoring, logistics, agriculture. The idea is that these AI systems, they really have the ability to understand the data that is sometimes generated by multiple sensors, by multiple inputs. They're also able to make prediction. And in the case of maybe automotive car, for example, we even rely on them to take action. What is very important in our era today is that these AI systems, they are deployed not only on computers, but really on Internet of Things devices, so wearables, smartphones, etc. The real challenge is that as we progress in time, AI models, they are becoming increasingly powerful, but also very complex and power hungry. What you see on this graph is that the training costs of neural network models, like large models, they really have been increasing exponentially as the time passes. So this has two consequences, and the first consequence is that there is really a need now for high-performance computing that supports the training and the computing, the execution of these large AI models. The typical model for this, or the typical deployment for these models is that you have your computer, you send a request to the cloud, so you send a request to a data center, and there you have, of course, a high training cost in the initial phase of your deployment, and then also a high usage cost. But then the second problem is that as soon as you start deploying artificial intelligence on Internet of Things devices, on wearable devices, on mobile devices, you then face really additional challenges. Let's say we can cite 3 of them. The first is that if you start sending a lot of data from your device to the cloud, you may face the problem that you have a limited bandwidth. So you may face latency. In the case of autonomous driving, for example, it's then a critical issue. If we are talking about devices running on battery, then you also face a problem because you spend a lot of energy to actually send data to the cloud. Maybe this data is not even useful. So this is really a waste. And another concern could be also the question of a limited data privacy. Maybe you are sending sensible health signals or whatever is should not fall in the hand of anyone. And one way to address this challenge is actually to deploy AI directly, locally, on the chips, on the devices. And this is what we call edge AI. Edge really means that we are really on a device that is remote. But this, again, it quickly faces constraint in terms of energy resources. Just before, we talked about the fact that it costs energy to send data, but actually it also costs a lot of energy to compute neural network directly on chip. So in the next part, I will try to give you a quick introduction to how mathematically artificial neural networks are defined so that you understand also why it is computationally intensive. So we will go a bit more into the details of mathematics. A deep neural network, it structures into these layers of interconnected nodes, that we also call neurons. And here we talk about the vector X, which will be the data that we want to analyze. It is presented at the entrance of this network. So here it can be, for example, the data contained in this pixel of this tiny image. Then from each neuron, the signal it is sent to the neuron of the next layer. So through each connection, what is very important today to grab is that the signal is multiplied by a weight. So this weight, it represents the strength of the connection between two neurons. And by analogy with the brain, the nodes, we say that they actually represent the neurons, and the weights, they will represent the synapses. A bee, for example, it has a very tiny brain, it has 1 million neurons, but in comparison, a large AI model like GPT-4 has like 100 billion neurons, and it has over 100 trillion synapses. So this is what we mean by large models. So an artificial neuron, then it can really collect and receive weighted signals from many connections, and these signals, they are really summed up at the neuron. This is why between each layer of the neural network, we really talk about multiply and accumulate operation. For those who are good in mathematics, you understand that it's also a vector matrix multiplication, but I don't want to confuse you today. So we will really talk about this multiply and accumulate part. And then the question is, how do we actually compute these multiply and accumulate operations? And why are our computers maybe not the ideal hardware for this? Then I go also a bit more into details. So in a conventional computer, well, each multiply and accumulate operation, it requires quite some steps. It requires first to fetch the input, the weight, the partial sum from the memory where it is stored, to fetch them, to bring it in the processor where you will have the multiply operation and the accumulate operation. But of course, you can only do this sequentially. So you have to write back this updated partial sum back in the memory and repeat. So you see that this data transfer between the memory and the processor, it actually dissipates a lot of heat, it consumes energy, and the heat dissipation is not only a problem in terms of energy, but it's a problem in terms of latency, because you basically have to wait for your chip to cool down, let's say, to continue the processing. It's not really a matter anymore of how performant is your computer. It's really a matter of bottleneck between the memory and the processor. So we really understand now that avoiding this energy dissipation is really critical to the deployment of AI. And if we think about it, nature is actually a good model. It's actually running neural networks with a very small power. And if we take again the example of the bee, of course it's not able to perform complex calculation, but with its 1 million neurons, it's actually able to navigate, it's actually able to adapt to new environments with only 1 milliwatt. And the main difference between the previous architecture that I show you and a brain is that in the brain, the memory and the processing are co-located. So you have the neurons that compute the addition, and they're finished or terminated by synapses, where the multiplication is performed, and that also takes care of remembering or taking care of the memory part. So the concept behind neuromorphic electronics is really to take inspiration of the nature, and is really to support computation of neural networks using hardware that mimics, let's say, the principle of biological synapses and neurons. So let's talk first about this multiply and accumulate operation that I introduced in the introduction. So the multiplication part, in fact, I hope many of you here are electrical engineers and know about the Ohm's law, but I guess you're also learning in high school. So in high school, we learned that the relation between the voltage across a resistor and the current that flows across the resistor is actually this equation, which is a multiplication. In high school, we also learn about the Kirchhoff's law, which says that when you have a node where different current flows in and out, the sum of the current that flows in is equal to the sum of the current that flows out. So this is an electrical analog implementation of the addition. So here I will go a bit fast, but you can't believe me. The idea is that this multiply and accumulate operation, you can perform it in only one time step, by a parallel voltage drop through a crossbar array of resistive, so ohmic elements that satisfy the Ohm law. And again, the sentence here that I highlighted, the fact that it's performed in one time step, is really important, because we saw before that in a von Neumann computer, the calculation is sequential. So here you can really accelerate the computation of neural network. But let's talk about the requirements on these resistive synaptic weights that we need to develop to build this kind of system. These resistive synaptic weights, they need to do 4 things. They need to store the information, their memory. They need to be integrated in an electronic circuit. You cannot just have them stand alone. They need to exhibit this ohmic relation for the multiplication. And of course, you need to be able to program them in a large number of conductance states. So I didn't learn this at school. The person who told me this is Jean Fonperheim. I met him in the Oxide-based electronic conference in 2018. At the time, he was working with IBM Research Zurich. So we discussed a lot. At the time, I was working on a kind of material that is ferroelectric materials. So ferroelectric materials, if you never heard of it, it's a very interesting class of materials. They are structured into domains that have a spontaneous electrical polarization. It means that when you turn off the electric field that is across this ferroelectric material, the electrical polarization remains. And this is very interesting because the configuration of this domain is really non-volatile. Once you program a ferroelectric, it remains until you apply another electric field, which means that they are very good candidates in general to act as non-volatile memories. So they can really store the information. And why did we talk about ferroelectricity with Jean? Is because, in fact, in 2011, there was a metastable ferroelectric phase that was discovered in hafnium oxide. And hafnium oxide, it's a metal that was really widely used as a dielectric material in the industry. So it was used as a dielectric, not a ferroelectric. But as I said, this discovery made, let's say, a new interest in ferroelectricity from the industry. So then there are, let's say, two other points that we need to address if we want to be sure that this ferroelectric material can be a good candidate to implement these resistive synaptic weights. The two other points was that, again, this has to implement this multiplication through the Ohm's law, and that we have to program these devices in a large number of different conductance states. Here I will go a bit slowly. This slide is a bit technical and a bit out of the flow from so far. So this is the work that I was doing in my PhD thesis quite a long time ago. But it's just to show you the inspiration that I got from my previous work at the time. So I was not working on neuromorphic applications at all. I was not working on analog AI. I was also not trying to do memories. I was trying to do devices in which we had a superconducting channel and on top of it, a ferroelectric material. And what I was trying to do is to induce different conductance states in this superconducting material. So really during these 4 years with my PhD co-advisor, Javier Villegas, I was trained or taught about this concept of having ferroelectric field effects between a ferroelectric material and an oxide that is next to it. We're really trying to have these perfect defect-free interfaces where this ferroelectric field effect could propagate, let's say, in the electrode material. So in my lab, there was I had another PhD advisor, which was Dr. Manuel Vives. And he was working already on a concept that is a bit more applicable to the one that we are looking for the resistive synaptic weights. It's the same idea. It's the idea of having a ferroelectric field effect. But this time, he was working on a very, very thin tunnel junction made of a ferroelectric material. And what he showed is that if you are now changing or flipping the ferroelectric polarization, you can actually change the probability that an electron can tunnel through this material. So really the key message here is that using this perfect epitaxial single crystal material, he was able to demonstrate this idea of having multiple conductance states in a device which was done in a non-volatile way, which you could really control with also a large number of intermediate configuration. So from there, I asked myself the following question. Do we actually really need these very perfect, atomically sharp interfaces to get this functionality? And can we actually imagine a CMOS-compatible ferroelectric synaptic weights that behaves the same way? So this question, I also tried to address it with Jean and also with Mathieu Luzier, who was already at ETH at the time. This was in 2019. And we submitted a proposal to the Marie Curie Action. The name of the proposal was Ferroelectric Resistors as Emerging Materials for Innovative Neuromorphic Devices. And the concept that we proposed was the following. It was simply to have an ultra-thin ferroelectric thin film, in green here, which was made of hafnia. The idea was really to leverage the fact that because of its unique fluoride structure, I go a bit into the detail of the chemistry, actually, ferroelectricity is possible in this regime of 3 to 5 nanometer thick. So it's a thickness that is compatible with electron tunneling, and the idea is really to reproduce with CMOS-compatible material the concept I showed before. And then again, to have this, low and high resistive state, we need an asymmetry somewhere. So we propose simply to investigate different metal oxides that we will put at the proximity of this ferroelectric material to really create just an asymmetric energy profile depending on the ferroelectric polarization direction. So this project was funded, and I really thank again Jean and Mathieu for helping me through the proposal and then through the realization of this project. So this approach was actually successful. In 2022, we could demonstrate a ferroelectric synaptic weight. So to go a bit more into the details of the materials, it was not pure hafnium oxide, it was actually a solid solution of hafnium and zirconium oxide with the metal oxide that we chose was a tungsten oxide interlayer. I will tell a bit more about tungsten oxide in the next 2 slides. So what you see on the big graph here is the typical results of an experiment where we first send the programming pulse. Here it's a 20 nanosecond long pulse that has an amplitude that goes, as you see, a bit slightly above 3 volts. And after this programming pulse, we read the conductance of the junction, but in a non-destructive way. This is quite important. So what you can see here is that we have a very nice reproducibility, a very nice switching from a high to a low resistive state, going through a very large number of intermediate configuration. I think the cycle-to-cycle variability is also very important for the functionality. It really means that we have, let's say, a reliable ferroelectric synaptic weights. For this part, there are many people I would like to acknowledge at IBM Research, but I will really shout out to Mathieu, who really helped me developing the materials, really worked with me in the clean room many hours, also worked with me long hours in the electrical characterization lab to build the setup that was able to really characterize these synaptic weights. So I promised that I will talk a bit about materials. And here I want to also highlight the fact that we had success with our technology also thanks to this tungsten oxide interlayer. It's actually very important for 2 things. First of all, we found that it has a very important role in the fabrication part because it actually helps the hafnium zirconium oxide to crystallize. When we grow it, it's amorphous, and to get it in the ferroelectric phase, we need to crystallize it. And we need to crystallize it in a phase that is metastable. So it's not so easy. And really thanks to this tungsten oxide layer, we were able to not only crystallize thin films, but to crystallize really ultra-thin films, so below 3 nanometer. So you can check this publication if you want to know more. Then the tungsten oxide, it has another important role, this time in the mechanisms that, let's say, drive the resistive switching. So we found that, in fact, during the ferroelectric switching, there was also involvement of the oxygen atom that were maybe transiting from the tungsten oxide layer to the hafnium zirconium oxide layer. Using temperature-dependent measurements, we also showed that we have this ohmic conduction that is desired for the functionality. So to summarize so far, I show you that at IBM, with this Marie Curie fellowship and also a bit later, we developed this technology of resistive synaptic weights. We saw that it fulfilled 3 of the 4 criteria that I mentioned before, that they were able to store information, to exhibit ohmic conduction, and to be programmed in a large number of conductance states. So let's talk now about point number 2. How do we actually integrate this material in an electronic circuit? So, for those who don't know how electronic circuits looks like, this is a schematic cross-section of what we call the CMOS technology. It has on the lower part the active transistors, so all the doped silicon that allows you to really have the functionality. It's what we call the front end of line, and it's typically also where we would design the neurons. And then on top, we have several levels of passivation layer, metallization layer, that really allows you to connect all these devices together and really create the circuit. So in 2020, I think, we started the Biferosynaptic EU project. Biferosynaptic is for back-end-of-line technology platform based on ferroelectric synaptic devices for advanced neuromorphic processors. And with this project, we were really lucky because we had the chance to receive from a foundry CMOS wafers that were not fully processed. So they accepted to basically do engineering runs, stop the fabrication at this metal 4, basically, and to send us these wafers so that we could try to really build and integrate our technology on top of this CMOS circuitry. So I would really like to thank X-FAB also for accepting this, because it really means that they are involved in research. So there are two challenges. The first challenge is related to our material. Our material, we develop it on silicon, and it's already quite difficult. But then if we start to putting on a substrate that is rough, that has a different just thermal behavior, then things become always complicated. So this is the first challenge. And our second challenge is for the CMOS, because the CMOS is actually quite fragile. And there is a rule, let's say, that you should really not exceed 450 degrees to protect these CMOS. Some are worst, some only need 350 degrees to break, some are a bit more robust, but that's a rule. The problem is that, as I mentioned before, the ferroelectric phase is crystalline. We need to obtain it, and we typically obtain it by a high temperature annealing step. So this is really required, and it's kind of incompatible with this concept of CMOS technology. So we tried on our hafnium zirconium oxide thin films. It was not working. So in fact, we really needed more efforts on the materials to go to, let's say, integrate the technology we had on this CMOS. And then here I go a bit into details of materials. I will try to explain it in comprehensive words. As I said, we are working on a combination of hafnium and zirconium oxide in a solid solution. And in fact, zirconium oxide, it has a lower crystallization temperature than hafnium oxide. It's not ferroelectric itself, it's actually another phase, which is also interesting. But the whole idea, if I try to summarize, is that by creating volumes of zirconium oxide that were a bit bigger, we will create some seeds for the nucleation that will facilitate the whole crystallization. So we explored this technique, and it actually worked very well. We also could play a bit with the parameters. So now that we decided to have superlattices or nano layers of different thicknesses of hafnium oxide and zirconium oxide, we could also play a bit with this period, so how thick will be the interlayer. And as you remember, I also mentioned the very important role of tungsten oxide layer. Tungsten oxide, we could also optimize a bit its thickness. And still on silicon, I think we really achieved nice improvement compared to our technology developed with the solid solution. So a very important figure of merit is what we call the on-off ratio. So it's the ratio between the conductance in the high and the low resistive state. And here you see on this graph, in blue was the original solid solution device with an on-off ratio of 7. We could improve it to an on-off ratio of 32 as we go to this optimized stack. You also see that the overall resistance shifted towards lower resistance, and this has an effect on the scalability. It means that we can put devices that are 5 times smaller while keeping the same current level. So it was very interesting. And then in 2023, we really achieved what we wanted to do, so to really integrate these ferroelectric synaptic weights in the back-end of line of this X-FAB CMOS wafer that we received in the context of Biffer synaptic. So here, by playing a bit with this synaptic weight that is attached to an NMOS transistor, it was very interesting. We could demonstrate, let's say, 2 major things. The first part is that we could prove that this NMOS transistor could really act as a device selector. It's very important in the crossbar array because it means that we can individually address or program these synaptic weights. And the other part that we show, it's a bit difficult maybe to understand, but we show that thanks to the compliance current of the transistor, so just by opening more or less the gate of the transistor, we could actually prevent or allow the ferroelectric switching. So we could actually decide on how we wanted to program our synaptic weights. So here I would really like to acknowledge Stefan from NAMLab. He not only coordinated the EU project before Synaptic, but he actually also really went in the lab himself to measure my chip. So it was really great from him. Okay, so I give another additional summary to this first part of the talk. We show that our resistive weight technologies fulfilled these 4 key parameters that we discussed before. So in fact, what we showed is that the synaptic weights, they are a good candidate for this analog implementation of multiply and accumulate operation, which, as I said, could really accelerate artificial neural networks computation. So the question is, what is next? From here, we didn't really talk about the training of the neural networks. And this is really the question that we address now. Can we actually achieve really the learning with these photoelectric synapses? Can we have a way to have these weights that change as the neural network is trained? And this is really the subject that I wanted to address with my professorship. So the title of my project that I submitted to the Swiss National Foundation is Photoelectric Superlattices for Bioinspired Computing. And as Jörg introduced, it was accepted. I could join the Integrated Systems Laboratory earlier last year. I also want to thank again Mathieu for supporting me in this project, and also Monica, I hope you're here, to for helping me to start my group, also making my workplace really a fantastic place to work. So thank you. Then in the second part of my talk, I will start to show much more faces. I hope you will not get bored of it. Because I really want to show you that we actually need a whole team to achieve this transition from just going to inference of neural networks towards actual learning. I'm getting late. I hope I will make it in 45 minutes. So the lessons from the research that I know, let's say, on single crystal thin films to achieve synaptic plasticity is that we don't only need work and development in the clean room, we actually need much more efforts on fundamental research. We need fundamental research efforts on the microstructure of the thin film. The link is not obvious, I'm sorry. And we also need some research on the domain dynamics of the devices. So now I will show a bit what my group is doing. First of all, to really work on this idea of having a control on the microstructures, we are exploring the integration of ferroelectric hafnium oxide on crystalline substrates. So not only on silicon, but really on crystalline substrates, and if possible on materials that are interesting, not just the electric crystals. So for this, we rely on collaboration, and I would really like Nick for coming today, attending this talk, from PSI, who is growing very high quality single crystal semiconducting oxide thin films by pulse laser deposition. I would also like to acknowledge my colleagues from Leuven and from HZB in Berlin that are expert in molecular beam epitaxy, which is a technique that also allows to grow crystalline epitaxial oxides and crystalline oxides in general, but at the wafer level, which is also a very promising technique. So what do we do with these wafers and with these crystals that we receive? Well, it's a very hard task of Onwesha, who is doing the PhD with us, and Jajay, who was doing the master thesis with us. They really take care of doing the mass design, the clean room fabrication on this very exotic substrate with this super highly reactive material. But they really do a great job in this, and I would like to congratulate them. Again, I will make a shortcut. But really the idea here is that by controlling the microstructure, we can have much more control on the functionality than just having a non-volatile memory that you can program. You can really start to play with the way you want to program these weights, and you can really go towards biologically plausible learning rules. For example, Hebbian learning. I wrote in grade that I will need a complete lecture to explain why. But I think if you're interested, you can also, let's say, reach out to the group here of the Neuroinformatics Institute, who are really also inspiring all the research I do towards the more neuromorphic aspects. So I will close this parenthesis and go back to the field of analog AI. So let's talk a bit about analog AI. We talk about the fact that we need a control on the domain dynamics, on the microstructures and on the domain dynamics. What we are doing since 1 year is to also explore partial switching in scale devices. Here I would really like to thank Thiel for opening the door of his characterization setup, helping us to start with this. Also Alexandre, who was my first PhD student 1 year ago, and who did a great job in clean room fabrication and electrical characterization. So what he showed, thanks to his work and the setup of Thiel, is that in fact we were able to achieve the full switching of our device with pulses that were only 1 nanosecond long, which is 10 times better than what we showed before with these 20 nanoseconds. With a reasonably high amplitude, so with 5 volts that you can easily implement on a circuit. Then we have another, let's say, project, which is not only to compute with ferroelectric resistive memories, which actually dissipates still a bit of power, but with ferroelectric capacitors. It's quite an emerging field. I also don't have so much time to explain this. But the idea is that you can really save a lot of energy by just not dissipating this joule heating that you have for a resistor if you work with a capacitor. So for this, I would like to thank again also another person, Miklos, for the same reason. He also opened the door of his lab, allowed us to measure on a setup that was even faster, so we could go down to 20 picosecond pulses. It's a bit hard to understand. I will try to make it clear. But the idea is that when you apply this very fast pulse to a capacitor, you don't even let the device the time to charge. So you have a kind of transition from a capacitive response to a resistive response. And this is great because, in fact, you are able to measure if your device is polarized in one direction or the other just by measuring how much current flows through this capacitor in this ultra-fast regime. So we really understand well these results because it was consolidated by also simulations that our students were able to do to really, let's say, fit this experimental data. On the work on capacitors, I would also acknowledge our collaboration with the University of Groningen. I've been working with a long time with Beatrice Noeda, and his student Ruben came for a few months in Zurich, and it was really a pleasure to work with them. So I will skip one more time topic to also explain what we try to do at the circuit level. Here I was talking more about materials than devices, but what we do at the circuit level. So our pipeline, let's say, ideal pipeline is the following. We fabricate a ferroelectric synapse, then we look for a setup. So either Miklos or Thiel or the group in IBM, thank you always for opening the door of your lab. And then from the data that is generated with this experimental characterization step, the idea is to start feeding an artificial neural network simulator to see, okay, how will the chip behave if we would fabricate it. This is quite useful to accelerate the design of circuits. And for example, the thesis of Paul, who is doing the master with us, is to evaluate if there is a trade-off, for example, between sending short pulses, which will not necessarily give, let's say, the ideal performance, which will maybe slow down a bit the training of the network. But at the same time, short pulses would allow to have a very low energy for your training. So he's evaluating this kind of trade-off using this analog AI simulator. So having this kind of circuit level results is very important because ideally, the idea is that it really provides guidelines for understanding what are the key properties at the device level. It's really the idea behind co-design is that you will not only work on the device, but you also need to work on what it means at the circuit level, for which algorithm, and how to have this feedback loop where you will progress on the three aspects in parallel. So this is also the work that Nikhil, who just arrived in our group, will carry on. So welcome. Okay, one last slide to tell you about something else. It's related. But here we talk about circuit level implementation through circuit level simulations. It's not very exciting. And what we really would like to do, ideally, is a circuit level demonstrator. But of course, our group will never be enough for this. It's really a very challenging project. And for this, we rely on collaboration. So late in 2024, our project VIT-Fox started. VIT-Fox stands for Vision Transformer. It's a kind of neural network with ferroelectric oxides. It's a very exciting consortium. We have partners from Europe, Fraunhofer in Germany, Silicon Austria Labs, and the coordinator is from Democritus in Athens. But we also have, as you see, 4 partners from South Korea. So it was a very nice initiative funded by the CHIPS, JU, and Horizon Europe. The idea here is that really each of the partners will work on one aspect: algorithm, circuit design, test boards, neurons, electronics. We will really focus on materials and integration. And I would really like also to welcome Alexander and Nathan, who also just started their PhD journey. Alexander will work more on the heterogeneous integration. Nathan will work on the exciting concept of ferroelectric channel junctions, leveraging atomic layer etching. So this is for the future. I will now try to give you a little summary of the little milestones that we discovered today. So I kind of explained that it all started with, let's say, my experience in field effects, ferroelectric field effects, in single crystal, perfect, complex oxides. Then I had to transpose this concept to, let's say, more realistic ferroelectric analog resistive memories with hafnium zirconium oxide. Then we made a big progress towards the CMOS integration of these synaptic weights. And finally, we are now, let's say, controlling much more the ferroelectric switching dynamics. As I said, the ultimate goal is really the fabrication of these neuromorphic computing systems. So, of course, the reality is not that linear, and it looks more like this. But it's also what makes research very joyful, I think. So I would really like to thank, first of all, my parents and partner, Maxime, who came to watch this talk today and who were really with me all this path. And of course, you all. I will not start to cite people because it will make a long list. But yeah, thank you very much. Jörg mentioned that I will say there will be something, so there will be an apéro just there, I think, behind the Audimax. So you're very welcome to grab a cup of wine or water, food if there is enough. So yeah, thank you very much.